Okay, hello everyone. My name is Louis Daguerre. I'm a VP Marketing at AGT So today we'll have a short webinar on the use of 3D vision for robotic process control. This is one of a series of many webinars. Actually, we'll have one also tomorrow on a robotic welding application for bridge cross frames. So if you want to join us, it will be around the same time. So if you want, we can send you a link on this one as well. So back to today's webinar. So what we have for you today is we'll present a little bit, a few minutes on AGT Robotics, who we are, what we do. And we'll go through a few important concepts for 3D vision. We'll go over a few 3D technologies, so cameras and scanners. And we'll give you a few examples of 3D vision. On top of that, we'll also show you a few examples on how we use vision for the welding applications, for example, seam tracking or seam finding. See, hello? So I don't know, we might have a few sound problems at this time. Okay, give us a second. We'll just figure out if people can hear us. Okay, so I think this is good. So we'll continue on this. Okay. So a few words about AGT Robotics. We are in business since 1992. We have hundreds of automated systems installed in Canada, USA, Mexico, some soon in Australia, in Europe. We have two plants, one in an hour east of Montreal and another one where we have programmers working in the Montreal area, and a large network of partners. Actually, today the seminar is also sponsored, also done in collaboration with Praxair, who distributes all of our product solutions and custom solutions in Canada. So our main focus is for the following industries. So of course the metal industry, so fabricated structural metal, foundries and forging, boiler, tank containers, pressure vessels, heavy fabrication, machinery, and engine, turbine, and power transmission. So our real focus and our mission is to help our manufacturing customers to successfully implement robotics, especially in low volume, high mix production. And that is where the vision systems take all their readings, since you can use vision system to look at the part and basically adapt the robotic path based on what the system just saw. So I'll guide you through a few important concepts in 3D vision. The first concept is topography versus color. So if you have only a true 3D system, well, the 3D system will sense dimensions, so X, Y, Z. But if you want to look at color, then you need additional sensors. Some sensors do both, but at its core, it's only doing 3D representation. So it's a point cloud or a 3D image where you have no sense of color. When you see an image like this, where you see like a color map, this is just, the system doesn't actually look at those colors. This is just a map for us human to look at the 3D image and have a better sense of what is high and what is low. So in that example, red is high and green is low. Another important concept is working distance. So unlike like 2D cameras where they have you can see an object really close from the camera, or really far from the camera, most 3D sensors will work only at a certain range. So, for example, in this example, since it's a triangulation between a sensor and a laser that has been emitted, there's a minimum distance where you actually see nothing, because the laser has to hit the object in order for the camera that is at an angle to see it. So this is also an important concept when you select, you're trying to find the right technology for the application. Another important concept, of course, is field of view. So the same camera, the same sensor, put at a different distance, can see a different field of view. The example I always give is if you look at your iPhone or your smartphone, even though it's just a 2D camera, well, you can point at it at a certain object, and you will see only close objects. With the same camera, if you put it in a different way, you can look at an entire city and do a different job. Of course, the resolution will be different, and that's our next concept. Is the resolution. There's many type of resolution. You can use a native resolution of the CCD in the camera, the spatial resolution. So basically, in the real life, what is the minimal feature you can detect? This is probably the most important feature. So if you're trying to follow a joint in welding, well, you need a pretty good, probably a sub-millimeter resolution in order to correctly guide the process. If you're looking at other application where you can have only a few centimeters or even a few inches, then it's a different story. So you need this, once again, the same camera could have a different field of view, thus a different spatial resolution. A few 3D technologies available. So once again, same thing with resolution. So there's not a better resolution than another one. You just need the right resolution for the right application. Because basically, typically the more resolution you have, it's like a TV. The more resolution you want, the higher cost will be. And sometimes you don't need it in a certain application. Same thing with the 3D technologies. There's differences between the 3D technologies, but you need to find the right one for the right application. First, for technology, of course, probably the mostly used is the triangulation laser scanning. So basically how it works, it will automatically analyze the distortion of a projected laser line on a moving body. So these are really fast technology, pretty easy to adjust. Some 3D cameras come with already pre-calibrated systems, and it's really suitable for industrial environments. The con side about it is that it requires controlled motion, and it requires a great computing power. And when we say controlled motion, it's the example I always give is for those of you who are old enough to have seen fax machines or even photocopiers, you need a coordination between the movement and the scanning unit. If you move the page on a photocopier while the system is moving the scanning device, well, you'll have distorted image and thus probably bad results in terms of industrial system. Well, industrial system works exactly the same. Second 3D technology, basically it's the exact same thing. So it's a triangulation laser scanning, but instead of moving the part or the entire body of the scanner, there is a motorized mirror inside the scanner. So as seen by someone on a factory floor, you would look at a scanner that is static. You will look at a part that is static. But the scan will the laser line, you'll see actually the laser line projected on the object that will move. And the movement is actually controlled in an automated way inside the scanner box. So this is pretty easy to install in an environment, in an industrial environment. But once again, the object has to be static. So, for example, there are applications where the object is on a conveyor and cannot be stopped. Therefore, you would have to use the first technology, the laser scanner. But sometimes the object is just static on the floor. If you want to scan it, well, it's easier to use that technology that doesn't need any movement either from the scanning box or the object. As we said, limited field of view, that's a con side as well, because you have to live with the limitations from the box, from the scanning box. When you use a triangulation scanner, of course you have a field of view on the transversal side, but on the longitudinal side you can have an object that is unlimited in length, because the object is moving and the scanner is static. In that kind of application, well, you have to live within the scanning box or the field of view. Another technology is time of flight. That is quite new technology. Basically, it creates a point cloud by emitting a pattern of light and then calculating the time that this pattern takes to come back. And for each, so basically it's using a known factor of the speed of light, and it will generate a point cloud associated to it. They're very, very nice features. The fact that it's very fast, so you get 60 point clouds, so 60 3D images a second. It can work with really long working distance up to 10 meters, and it's really suitable for industrial environments. It's actually the technology that is used in Microsoft Kinect, for example, and so it has a lot of application, for example, when the resolution is not needed, because as you can see, the con side about it is that it has a very low resolution, typically 160 by 120 pixels. So if you look at a palette, for example, of 48 inch by 48 inch, it's typically sufficient for palletizing applications, for example, but would not be sufficient to do seam tracking or to find a joint, for example. So roughly it has a precision, especially in the z-axis, of plus or minus 1 centimeters. It's actually also a technology that is used for AGV, automated guided vehicles. So it can be like a quite fancy sensor to actually look in front of him and know if there are obstacles coming, because you have a refresh rate. There's a new image every 1/60th of a second, so it's quite fast to have some good feedback. Another technology is stereography. So basically, it's two cameras looking at the same object from a different perspective. So that technology really tolerates different surface finishes, and it's quite a low cost because these are pretty standard camera. However, it requires great computing power because you have two images coming in and they have to figure out what are the common features in both images, and that way they can create a 3D image. And also the most important thing is you need a geometric landmark in the subject. So for example, if you would use a stereographic camera just to look at a white wall, it would probably be the best setup for a laser scanner or even a time of flight, but the worst one for a stereographic, because there's absolutely a total white surface with absolutely no geometric features in it. So there's no, the system cannot look at the same feature and compare it. So it's more difficult. But it has some applications where, for really complex objects, that can be a really nice technique. There's also mostly used in metrology for inspection purposes, the white light 3D scanner. So basically, how it works, it will analyze the deformation of a pattern of light projected onto a part. So typically, that's the the technique that will provide the highest spatial resolution and with a relatively high field of view. However, once again, it requires a great computing power. Um, some of you may have heard that, like the white body inspection. So it has a low tolerance to surface finishes. Sometimes you actually have to paint the part in a different color, like usually white, very matte white, in order to make it work. And the part must be static. Also, these are very expensive techniques. As I said, they're mostly used in the automotive sector for metrology purposes. A few applications that the AGT has done in the past using 3D vision. I'll show you a few. So first one, that's the Beammaster Fit and Weld, so a complete 3 robot solution where we import the information from a 3D CAD, and all the operator has to do is provide steel to the machine. So beam on one side, as you can see, and the accessories on the other. So in order to compensate for the fact that the robot trajectories were generated using perfect information in the CAD, well, we have to scan both the accessories and also the entire beam in order to compensate all the programs and actually position the accessories at exactly the right position on the beam. So all the movements you see there are done entirely automatic and were generated by software developed by AGT Robotics. Another application that is actually the prototype unit. That the real one is a little bit confidential in the way it works, and it's installed here in Quebec, and it has been in production for almost 7 years now. So basically what we do is we use, once again, a laser scanner in order to scan the entire part and then modify all the robot trajectories that were programmed using an offline programming tool in order, once again, to compensate for the tolerances of the real parts. In that case, the real part is as big as, it's much bigger, probably a diameter of close to 20 feet. So and it's a huge turntable instead of that small one. And basically it's a hydraulic turbine, and the system will scan the entire hydraulic turbine. Will take many minutes, and then crunch all the data to generate and modify the trajectories. So that's another application. Another one, once again, using 3D scanning, also for a good mix of resolution and cost. Basically what it does, these are steel elbows, and the system scans side A and scans side B and automatically generates the cutting trajectory custom to each part, because these are forged parts, and while they're being forged, they get quite out of dimensions. And before that company bought the cutting robot, they had tens and tens of hours of grinding time just to grind part A, grind part B, test them, re-separate them, then grind some more, mark them, and so on. So it was huge amount of time just to fit them together and prepare the parts for the last step, which is welding. But now basically, so they wanted a grinding robot, and we sold them a cutting robot, because we said if we add 3D vision to it, instead of just grinding, measuring, and then grinding some more, we can virtually fit side A with side B and generate the custom robotic path, cutting robotic path that is right at the first try. So that's what we did for that. Another application for using a laser scanner. Once again, this was an inline application for painting. So parts are dropped on a conveyor pretty much randomly, and the system will scan in 3D and will generate on the fly every 30 seconds a new painting path that will cover both the contour and the surface. And the surface is done both in the x-axis and the y-axis. So this has many applications also for painting, but we can also use the same technology for many other applications. If we go back to welding, one of the most important thing in welding, apart from applications where you actually have a jig in the parts and the joints are exactly at the right position, well, in the low volume, high mix, typically you want to avoid as much as possible the use of jigs. So if you avoid jigs, that means that the accessories can be at different locations, typically pretty close because they have to be in the right tolerances. But sometimes you can have tolerances of plus or minus 1/16, 1/32 of an inch, and that is enough to make the difference between a poor weld and a quality weld. So typically what a robotic system has to do is each time before actually executing a welding routine has to find the right joint at the right spot. So of course there's the jig technique, which where the robot can start immediately. You have the touch sensing or the nozzle sensing technique that are quite common, where you actually use the wire or the nozzle to find the walls, the side walls, the base, and then compensate, modify the robotic program to execute the weld. But what I'll focus on today, and that'll be the last 4 or 5 slides, is that we can also use 3D vision and to find the joint. So, for example, you've seen touch sensing. Well, this basically the exact same concept can be done with a laser. So basically, it would be the exact same thing as having a super long wire and touching with it, but instead of having a wire, you have a laser dot. So that's one technique. So basically, so the applications, that's pretty easy to integrate, and it can be faster. Why we're using it, it's much faster than touch sensing, and you can also be independent from the welding source. Something to watch for, of course, is surface finish. If you have a very reflective surface, it could lead to problems, and that's actually true for any 3D camera using sensor. You can have also basically a 2D camera, but actually it's a 2D camera used in a 3D way. So instead of just focusing on one dot, you have an image of the entire area, and then once again, as I said, the part doesn't have to be precisely located. So this is really a high precision and high speed application. Once again, things to watch for: surface finish, programmer skills. So you kind of have to position your camera in order to have the right field of view, and of course the joint access. The more you add cameras and boxes around the tool, well, it could mean that some joint you cannot access them because there would be a collision between the camera and the part itself. You also have real-time scene tracking. So basically, the way it works, once again, it's a 3D laser scanning that always looks a few inches before your welding torch, and basically it tells the robot what's coming. So if you have really long joints where the parts are the same but not really repeatable, that can be one of the good techniques to use. So basically it helps the robot to remain in the joint while welding. Once again, and this is really a high precision technique. Once again, the surface finish, the joint access are things to watch for. And also if you have a really tight radius or sudden changes in the joint, that can cause some problems as well. So at this point, I will thank everyone for listening. If you have any question you can use in order for, since there's many people on the line, if you can use the chat module, I'll look at it for the next 2 or 3 minutes, or as long as there are questions. And if not, I'll thank you. And I'll also would like to thank our partner Praxair for this webinar. Okay, we have a question on shiny surfaces. They say, wouldn't that technology work on stainless steel and aluminum? Yes, of course. It's also the shininess can also work with the angle. It's just that the more shiny, it's not an on or off kind of thing. Basically, if it's just a perfect mirror, then there's only one angle where it can work, so that's really not a perfect surface. But typical stainless steel with somewhat of a made surface and aluminum work fine as well. Okay, I think we have another question, I think, from Leon. If you're still there, I think if you talk, we'll be able to hear you.
Yeah, I can hear you. Can you hear me?
Yes, I do.
Excellent. Thank you. I have a question about your scanning plan that you use on your grinding robot and the welding robot. I'm kind of wondering a little bit about the background programming. Are you brute force programming? Are you have an optimization software running back there? Can you elaborate on that?
Yeah, there was quite a bit of software involved once we have the point cloud. We also asked a little bit of help. I think you saw it. I don't think I can actually show it in the video. If I go back to that slide. This one. Yes. So in the video, you'll see at one point we have a HMI where we ask this one. So we asked the operator to enter the right data because they absolutely had no CAD for that application, but they had thousands of combinations of radius, diameter, thickness, type of material, and so on. So basically, we asked them to provide us with some information on the green, red, and orange area, and from there, we would just do a match between scan A and scan B, use some libraries, 3D libraries, and find the right path that would optimize the fit between the two sides. So it was our own basically development in terms of using off-the-shelf libraries, but we still had quite extensive work to do to analyze the point cloud and come up with the right solution.
So just to be clear, this robot is scanning the raw part, plasma cutting bevels, and then finish grinding the slag to meet basically its mating parts profile, right?
Exactly. And all that with the tool changer, so it's the same robot that will drop the scanner, go pick up the plasma torch, and then drop it again and change it to the final the grinding wheel, just for the final deburring.
Wonderful.
Okay, thank you. Okay, I have another question. People ask how to define what is the most appropriate vision technique for a particular product. I think it all starts with speed, cycle time, and the actual mechanical setup. So do you want the part, sometimes it's easier, even if the part is static, sometimes you want to, actually, for example, I talked about the 3D scanner with a motorized mirror. So that has a certain field of view. If it doesn't cover all the part, then you have a choice. You can either move the part, rotate the part to a second station, and then take another snapshot if you want. Or you can duplicate the scanner, either move the scanner like we do, like you've seen in that one. We actually move the scanner to add the passes together with the robot. Or you could, for really fast application, you could have also an array. You could have 2, 3, 4 cameras that just snapshot the object together, and then so that is a little bit why part of our expertise is just to juggle with all those techniques, and there's pros and cons, and sometimes we can go from one setup to another, and sometimes price can be an issue, resolution, so there's basically the concept I've mentioned. Uh, Sometimes there's 2 or 3 or 4 different setups that are almost as good one to another. So that is a little bit how we decide for a vision technique. Sometimes some vision technique will basically eliminate themselves just because they're not fast enough, but that's part of the things we do. Okay, so once again, I'd like to thank everyone who's assisted to that webinar. There'll be another one tomorrow for robotic welding on crossframe. That will actually be a live webinar on our shop floor where we'll actually see the robot working with, once again, a low volume high mix, knowing that cross frames there's many different combinations possible. So we'll show you a little bit what was the challenges and the solutions we came up with, and we'll actually do a real demonstration on our shop floor live. So if you want to be there tomorrow, just send an email to info at AGT-group.com, and we'll send you the link for the invitation. So once again, we'd like to thank everyone from Praxair who has been helpful in organizing this webinar. Thank you.